Hello viewers, I am Kausalya. Today we are going to see the derivation of evaluation of generalized error coefficients. We know the formula, that is Laplace transform of f of t is equal to f of s. So by the definition of Laplace transform, here this f of s can be written as integral of 0 to infinity f of t into e power minus st into dt. This is the basic formula. Right. The next step, we are going to take limit s tends to 0 on both sides. When you apply limit on both sides, here you look carefully. Here we are having t term and here also t term, and here we are having an s term, right? So this limit s tends to 0 can be applied only to this exponential term, right? So therefore I am moving this limit s tends to 0 inside like this, that is f of t limit s tends to 0 e power minus st into dt. Right. So what happens when you apply s tends to 0? That is exponential term to the power 0, right? Because e power minus st, right? So e power minus, in the place of s I am putting 0 into t. So finally becomes e to the power 0, and exponential term to the power 0 is nothing but 1. So here this entire expression reduces to 1 here. So the remaining terms are f of t into dt. Here I am naming this expression as C0. So finally we can write C0 as, C0 is nothing but, you see here, this C0 is nothing but limit s tends to 0 f of s. So here I am writing that C0 is equal to limit s tends to 0 f of s. Right. So this is our first term C0. The next step is, again we are taking the same formula, f of s equal to integral 0 to infinity f of t e power minus st dt. The next thing is we are going to differentiate. So when you differentiate, what happens? This f of s becomes d by ds of f of s, and here this thing d by ds of integral 0 to infinity, you write the terms like this, right? So here again differentiation happens with respect to s. So f of t is a constant here. So the next step, I am moving this differentiation inside this integration. So integral 0 to infinity this f of t, and here I am having s term only here. So I am applying this differentiation. So d by ds of e power minus st into dt, right? So the next step, we are going to differentiate. So what happens when you differentiate an exponential term? You see this f of t is a constant, so it remains here as such. So when you differentiate e to the power minus st, this term remains the same, e power minus st. And again you have to differentiate the terms and the power. So when you differentiate the terms and the power, that is e power minus st, this s becomes 1, and finally we will be having minus t. That is, here I can explain you. D by ds of e power minus st is nothing but, here this e power minus st remains the same. So e power minus st you write as such, and the next step is we are going to differentiate the elements in the power. So when you differentiate, this s term reduces to 1 and the remaining will be minus t, right? So here that forms our next step, that is this f of t as such. When you differentiate this term, what is our answer? Minus t into e power minus st. Here I have written this, minus t into e power minus st into dt. Here the final step I have rearranged, that is minus, this minus I am taken outside. So minus 0 to infinity this t into f of t into e power minus st into dt. Here you see I had written the terms. Right. Here I have just rearranged the terms. Now mark this equation as equation number 2. The next step, again we are going to apply limit s tends to 0 on both sides. So when you apply the limit here, again this t and f of t are constant because we are dealing only with s term here. So now I am going to move this limit inside here. So when you move this limit s tends to 0 can be applied only to this part e power minus st into dt. Again, when you substitute the value of s as 0, e to the power 0 becomes 1. So here I am having the expression as minus integral 0 to infinity this t into f of t into this dt. Right. So I am naming this expression as C1. So I can write this C1 is nothing but limit, you see. This C1 is nothing but limit s tends to 0 d by ds of f of s. So here I am rewriting C1 is equal to limit s tends to 0 d by ds of f of s. Right. And the next step, I am going to again differentiate this equation number 2. You see, this is our equation number 2. I am going to again differentiate this equation. So when you again apply differentiation here, that is d by ds f of s, and here d by ds of integral 0 to infinity t into f of t e power minus st into dt. So here when you multiply, that is, this is double differentiation, right? So double differentiation, I can write it like this, d square by ds square. So here again to the right hand side we have to apply this differentiation. So when you apply the differentiation, what happens? Integral 0 to infinity t into f of t. Again here differentiation happens with respect to s, and here I am having this s term. So when you differentiate, what happens? The same thing. This e power minus st, you see on differentiation, the remaining terms remains the same. T into f of t into dt. T, f of t and dt remains as such. When you differentiate this term e power minus st, here you are having same e power minus st. But when you differentiate this one with respect to s, here this s reduces to 1 and I will be having minus t as remaining. So when you arrange the terms, minus into minus becomes plus here and t into t becomes t square. Right. So here finally I am writing as t square into f of t into e power minus st into dt. Right. Again the next step is, as usual, apply limit s tends to 0 on both sides. When you apply limit s tends to 0, here what happens? Again this exponential term reduces to 1 here. So, right? You see the same story, t square f of t, I am applying this limit s tends to 0 to this exponential term again. So when you apply limit s tends to 0 to this term reduces to 1 here. So here finally I am having t square into f of t into dt. I am naming this expression as C2. So C2 is nothing but limit s tends to 0 d square by ds square of f of s. Right. So here I had written this expression. C2 is nothing but limit s tends to 0 d square by ds square of f of s. Similarly, here we can write for C of n. So C of n can be written as d of n by ds of n into f of s. Right? You see, you replace n by 2, that is, in the place of n, if you have 2 means, we will get this expression. If we substitute n equal to 1, we will get the previous expression. Suppose if we substitute n equal to 0, we will get the firstmost expression. Right. So generally, we can write like this. Cn is equal to limit s tends to 0 dn by dsn f of s. Right. Hope you people understand this derivation. Thank you.